Hello. Imagine you're trying to master two subtle but critical skills at the same time. Determining if one newspaper headline is a paraphrase of another, and assessing if a legal premise logically entails a hypothesis. Seems difficult, right? But what if I told you that rather than training both tasks separately, training both at the same time improves results? The core task for both is the same: deep relational reasoning on a sentence pair. This shared fundamental structure forces the model to learn a more robust, general-purpose reasoning engine that immediately transfers knowledge from one domain to the other. This is the essence of multitask learning. The original 2019 Multitask Deep Neural Network, or MT-DNN for short paper, which first integrated BERT into an MTL framework, claimed that a shared encoder learns representations so robust and generalizable that significantly outperforms independent single-task baselines. This performance boost is particularly pronounced in low data settings. This Tiny Reproductions project was to verify this central claim under the most resource-constrained scenario possible. The MT-DNN model was designed to combine the strengths of language model pre-training and multitask learning. Its architecture features a shared bottom design, where the lower layers, specifically the BERT transformer encoder, are shared across all tasks. This shared encoder learns a universal semantic representation of the input text. Critically, this shared layer is fine-tuned using the objectives from all tasks jointly, which acts as a powerful regularizer, forcing the model to learn representations that are robust and generalizable across domains. The architecture is completed by separate task-specific output layers placed on top of the shared encoder for classification, similarity scoring, or relevance ranking. In the paper, the MT-DNN model is extensively evaluated across three popular benchmarks: GLUE, SNLI, and SciTail. As shown in the tables, the MT-DNN consistently outperformed existing SOTA models such as BERT on 10 natural language understanding tasks across these benchmarks. A minimalist design was adopted to isolate the effect of shared training. This strips away virtually all complexity. Two tasks were focused on out of the 10, task 1 being sentiment analysis using the SST2 dataset, and task 2 being natural language inference using the SNLI dataset. Crucially, training to only 1% of the original data and ran for only one epoch. This extreme low data regime directly tests the regularization benefit claimed in the original work. The MTL architecture uses a standard BERT-based encoder, shared between the tasks, and then split into two simple single-layer classification heads. Compared to the single-task ST baseline model, both models have identical parameter counts. The only difference is whether their encoders are trained jointly or independently. Here is an example of the inputs for your reference. 3 independent runs were executed, aggregating the accuracy results on the original full validation sets of the datasets, despite only 1% of the training being used. The results confirm the core hypothesis. Multitask learning produced positive transfer across both tasks. The shared encoder is better than the independently trained ones. The reproduced findings validate the central hypothesis. The trend holds. Joint training provides a powerful form of inductive bias that leads to positive knowledge transfer. Furthermore, the finding that the MTL model is more stable than the baseline was also reproduced, showing less sensitivity to the random seed. The absolute score of our model, 82.64%, is much lower than the original MT-DNN's state-of-the-art scores, which is expected. The low absolute score is due to extreme data reduction and simplification of architectural layers, such as SAN. However, because the 4% gain was achieved despite these massive constraints, the results isolate and validate the causal mechanism that shared training forces the encoder to learn robust and reusable linguistic features. This tiny reproduction successfully confirms that MTL produces a shared encoder that generalizes better than single-task fine-tuning, demonstrating the effectiveness of the MT-DNN's core design principle. The lesson is clear. Even small amounts of concurrent cross-task training can stabilize and significantly improve the underlying language representation. Thank you.